Hello, everybody. So we actually prepared a few polls so that you can give us some indications about your experience and about how you already use .NET and GPUs. So let's start with the first poll. So what is your actual CUDA experience? We would like to know, are you beginner, medium, or advanced? So you can actually add to the poll. We see that about 75% of the audience are beginners and about 25% are advanced. Now, the second poll, did you actually use Alea GPU before? And if so, with what language did you experiment or work with Alea GPU? So here it looks like that only very few did use Alea GPU with C#, and most of the audience has no experience. And now, third, what is the main interest of you in Alea GPU? Is it integration of CUDA in .NET? Is it GPU development with .NET? Is it CUDA tooling or the integrated library that comes? So most of the audience is really interested in GPU development with .NET. So that gives us a good indication about the audience and how we structure the examples later on and where we put the focus. First, I'll go through a few slides that you get the top-level introduction to Alea GPU. You know, GPUs are everywhere today. They are really revolutionizing high-performance computing and graphics. On the other side, .NET is becoming increasingly popular as a strategic cross-platform technology to cope with the growing hardware and platform diversity. And also, because of the recent open source strategy of Microsoft, .NET gained additional momentum. Developers can easily write scalable parallel code for multi-core GPUs on .NET. However, using GPUs to accelerate .NET applications is less straightforward. This is changed with Alea GPU. It brings GPU computing directly into the .NET ecosystem. Now, let's look at the main benefits of Alea GPU. First of all, Alea GPU is fully cross-platform. That means you can actually write GPU applications in the .NET framework, and they can be used on Linux, Windows, and Mac OS. The assemblies that you build, they are binary compatible. That means you build them once on one platform and you run them on any other .NET platform, either .NET Windows or Mono. That also simplifies, of course, deployment because you can deploy the same assemblies on all the platforms without any different versioning. The next benefit of Alea GPU is it increases your productivity. First of all, because as you will see later, we've integrated debugging and profiling fully in Visual Studio. So you can actually step through your .NET code that runs on the GPU and understand what's going on. And you can use the profiler to actually spot performance hotspots in your code and improve them. Another important benefit of Alea GPU is that it comes with a growing set of algorithms and libraries. For instance, in version 1, we added support for QDNN. In 2.2 that comes out shortly, we will have QREN and possibly other libraries as well. It's not yet fully clear. The set of supported libraries is continuously growing, and over time we hope that we can provide the same ecosystem that you have with CUDA CC++, which means that pretty much all of the important NVIDIA libraries are exposed to the compiler. That means they are not just wrapped to .NET. We also add a small layer so that you actually can use the same types that you already have in Alea GPU with these libraries, and that you don't need any further glue code to work with these libraries. So it's very convenient to use these libraries with Alea GPU. Last but not least, a very important feature of Alea GPU is that it increases agility, because you can actually do GPU scripting in the Visual Studio F# interactive console, and there you can repeatedly prototype GPU code. This is possible because our compiler actually supports just-in-time compilation, so that you can run scripts on demand. Alea GPU supports the following .NET languages. It supports C#, F#, and Visual Basic. It grew out of F#, so still the F# support is strongest. However, C# support is being improved radically over the last few months, and it's pretty much on par with F# support. However, there is still the debugger support for F# is still more advanced, but we will hopefully resolve that with CUDA 7.5 that will appear shortly. The supported operating systems are, of course, Windows, Linux, Mac OS. On the Linux side, we also support ARM, so that you can actually work with the Tegra Jetson kit as well. The integrated libraries that we have so far is QBLAS, QDNN, QREN in version 2.2, and more are scheduled for version 2.3 and later. So I would like to give you a bit of an overview how Alea GPU works from a compilation point of view. I think that's very important to understand. So you have C#, F#, and Visual Basic code. You have actually two compile streams. One is the IL compilation stream, which works for all of the .NET languages. And the second one is the so-called quotation-based compilation stream. So in the first compilation stream, in the IL-based compilation stream, we actually transform IL code with our Alea GPU compiler to LLVM IR. That's LLVM is a compiler platform, and IR stands for intermediate representation. So that's the main work of our compiler. Once we actually transform the IL code that should run on the GPU to IR, we then can use the NVVM compiler from NVIDIA to compile that to PTX, and this can then further be compiled by the CUDA driver once it's downloaded to the card to executable GPU code, to Cubin code. So that's the IL-based compilation stream. You see that first .NET compiler compiles, then our compiler takes on, and then the NVIDIA backend compiles it to PTX. So we have three compilation phases. With F#, we have an additional benefit, because in F# you can actually write so-called quotations. That is a unique language feature of F#. So certain code portions in F# can be marked so that the compiler also produces a syntax tree for you. And this syntax tree can then be further transformed to any other code. And that's what we do. We actually let the compiler compile our GPU code first to quotations, to a syntax tree, which we then further transform to LLVM IR, and then the NVIDIA compiler kicks in and compiles that down to PTX. So these are the two compilation schemes or schemes that we offer with Alea GPU. The quotation-based compiler is very powerful because it allowed us to integrate CUDA very nicely in F# as an internal domain-specific language. For the IO compilation scheme, we had to use some class infrastructure so that we could write kernels. You will see that in the examples later on how that works. So that's the compilation process of Alea GPU. So there is actually a question that I can answer. So the question is if Alea GPU uses Mono for Linux and Mac or .NET Core. So currently, Alea GPU uses Mono for Linux and Mac, but we are pretty sure that we can use .NET Core once it's been final, and we will certainly look closely at that. Good. So let's have a look at how the Alea GPU package structure looks like. So that's the next slide. So the Alea GPU compiler is available in multiple packages. So we have the Alea CUDA, and by the way, all these packages can be downloaded or obtained from Nugget. So the first package is Alea CUDA. This is the compiler core package. Then we have the Alea CUDA IL. It extends the core compiler with the IL-based compilation process. Then we have a convenience deployment package, which is Alea CUDA 40. This adds the ahead-of-time compilation tool. I will explain that in the examples as well. Then we have a library of performance primitives and all the integrated libraries that we expose. They can be found in Alea CUDA Unbound package. And then there is a helper package, the Alea IL, which is responsible for IL disassembly and also has some support tools which are typically not used by a developer. So if there aren't any further questions so far about the structure of the compiler and the packages, I can start with the examples. So the first example I would like to discuss is a very, very basic example, just to give you the flavor of how you code with Alea GPU. And it's a basic transform. So you have a large vector, and you would like to apply a function to this vector in parallel. So we actually have the traditional approach to map the block and threads to the data of our vector, of our input data. So here I schematically show the blocks, the thread blocks. I assume, by the way, some minor CUDA experience here. So you might know that you have your multiple threads grouped in blocks, and the blocks within a block, the threads can communicate and exchange data through shared memory. And blocks are scheduled to run on streaming multiprocessors. So here we do not need all that information. We just can assume we have a few blocks of threads, and each block has multiple threads. They are mapped to the vector elements. So here, thread 0 of block 0 is responsible for the first element of the vector. And once it has processed that element, it continues with the next one. So that is then number 12. Similarly, for thread 1 in block 0, it starts at element 1, and continues afterwards with 13 until all of the elements are processed. That's the basic idea of this parallel transform. So now let's look at the code. For this, I share my screen. I show you the Visual Studio implementation. So let's start with the C# version. Give you a bit of time so that the screen can synchronize. So here we do actually a very simple operation. We take the input elements and we square them.
Daniel,
so here is
I'm sorry.
Yes.
This is Allison. We are still seeing the slide, the getting started transform slide.
Okay.
There we go.
So okay.
There we go. Thank you.
Is it synchronized already? I think so. Right.
Yes.
Good. Okay, so I can continue. So here you see a simple reference implementation of what you want to achieve. So that's the CPU code. So we take an input vector, we loop over this input vector in serial, and we square the elements and store it to the output. Now we would like to code the same logic on the GPU as well. So for that, we need to write a kernel. A kernel function is an expression, is the terminology in CUDA. So that is a function which will run multiple times, once per thread, in multiple blocks, multiple threads. So all what you need to do is you actually decorate this function with an attribute. You tell our compiler that it should ahead of time compile this piece of code, which means it will take the IL code, it will transform these IL codes to IR, LLVM, and R. It will embed. It will then compile it to PTX, and it will embed these resources in our assembly so that it is ready for usage as soon as you would like to start this function. So that's the traditional approach, compilation approach, where you do everything at design time or at development time, as compared to just-in-time compilation, where you do it at runtime. So here, this square kernel gets three arguments. First argument is a pointer to the output. It's a device pointer, which means this memory is on the card, in the global device memory. It obtains the inputs as well in global device memory and the length of the vector. Then we have the usual CUDA primitives and symbols. Here the block ID. We can use the block ID and the thread ID to calculate the start offset, where we would like to start our computation for this actual thread. And we calculate the stride, which is just the number of threads in all blocks that work on the problem. So here is the loop. So the thread starts at its start offset. It loads the input data, it squares the input data, and it stores it to the output. Then we continue. We increment the variable I with the stride, and we continue until all of the elements of the array of length n are being processed. So that's the kernel function. The next item that we need is we have to call this kernel function from the CPU. And this is done typically with a launch function. So that's the glue kit between the CUDA code and the CPU code. Here we write another .NET function, square GPU. It takes a normal .NET input array, and it produces an output array, a normal .NET output array. So the first thing what we want to do is we want to grab a worker. A worker is a concept of Alea GPU. It represents a GPU and a CUDA context to work with this GPU. Here in this example, we just take the default worker, which is typically the GPU with the ID 0 that you have in your machine. So what you do, once you have the worker, you can allocate memory on the device and copy data from the CPU to the GPU. That's done here in this line. You actually use the iDisposable resource management of .NET, which is very convenient in this case because it frees you from explicitly deleting or kind of managing your resources. That's done for you. So here you allocate you create storage on the device, and you copy the inputs to that storage. Then you allocate storage for the output on the device, also with worker malloc, as same length as inputs. Then, with these two device memories, you actually start working. You first define the grid layout. You assume that your grid blocks are of an equal size of 256 threads per block. Then you do some logic to figure out how many blocks you would like to use. We use now just 16 times the number of streaming multiprocessors of your GPU. So that's the grid size. And then we define the launch parameters, grid size, block size. Once we have the launch parameters, we actually can launch the kernel. Again, we use the worker launch method. We pass in the kernel function here. We give the launch parameter, and now we use these device memories with the method pointer. We get the device pointer of the device memories for output, input, and we provide the length. This line then executes our kernel, and once it's finished, we can actually use the gather method to copy back the result from the GPU to the CPU. That's all what you need to do. So then you can create a small test function. Here what I do, I just use .NET to generate an array of input values. Then I call this .NET function, which internally calls the kernel, and then I write it to the console. So what I can do now, I can actually call this function directly here. I built the project. So let's look at the output of the build process. So we started to build the C# project, and it realized, okay, I had to, so Fodi plugin came in. It reports the compilation environment, so the operating system, assembly architecture. It reports us the compilation settings. Here we actually have set the compilation level to diagnostic, which means we create enough information for debugging and profiling. Tells us also that it actually compiles, ahead of time compiles two kernels, the parallel square kernel on the one side. That's the one that we just saw. And another one that we will discuss later, the generic sine cosine module kernel. And it embeds these kernels in the assembly as resources so that we can actually use them and call them right away. So what I can do now, I can put a breakpoint here, and I just can hit Start CUDA debugging. So here I am. So I'm in this kernel already. So important is that I will show you later on how to configure the compilation level in the different configuration files in appconfig or in 4dbeavers.xml. But now we can investigate the data. For instance, with the usual approach, we can pull out the workbench window. Out. Where smaller. I can add a workbench, for instance here, I, and inputs I. So I can start step through. So you see now my variable I for each of the threads in a warp have the values from 0 to 32 if I go down. And you see also the input values that I have in my inputs. If I continue stepping, you see how the next warp comes in. Now the next warp comes in with thread index 32 to 64 to 63, and you see the new input values. And with this workbench window, you can conveniently investigate your data and check if your kernel is working properly. Good. So I stop debugging again. So the next complexity is adding generic programming or programming with generics. This is done in this transform module example. Now here, I use a different coding technique. Alea GPU offers different coding techniques, 3 different coding techniques. The one that we just discussed is called the method-based coding technique, because you just need a function or a method, and you just decorate it with AOT compile, and that's it. The next more advanced technique is to use class instances. You actually use your ILGPU module class, you inherit from that class, and then you write your kernels as members of that class. The advantage of the class instance-based approach is that you can use generics and that you can solve more complicated problems. You have better software engineering capabilities. You can use delegates here. So what we do, we would like to pass in your transform function as a delegate with generics. So T, capital T, is a generic type argument, and func TTT is a delegate, which is in fact a binary function taking 2 arguments of type T and producing an output again of type T. So that's our operation. We create a constructor which, first of all, instantiates the base class with the GPU module target. That's roughly the compiled module that comes in later. And then we store our function kernelly. And we again write the kernel. The kernel is exactly the same, except we use now our op is a function. It takes 2 arguments, and it is generic. Then we code an apply method for convenience, which actually calls our kernel. It builds up the grid size, the launch parameters, and it uses the GPU launch member function to launch the kernel with the launching parameters and the inputs. Here we need 3 inputs, 2 for X and Y, and the Z for the result. Then we write a corresponding CPU glue function, which uses .NET array. These are generic .NET arrays, X and Y. We use, again, GPU worker malloc to store the X and the Y arguments on the GPU in device memory. We allocate storage for the result. Then we call our apply method from above. And we use rather return the values. Now, it is important to note that this function is still generic. This module here, this module class is generic. The function, the operation is not fully specified. So it doesn't make sense to use ahead of time compilation at this stage because we do not yet know the function. Once we would know the function, we can ahead of time compile the code. So that's what we do now. We create a specialization of transform module for type double with a very specific function. So you can use now delegates. And what we do, furthermore, we use libdevice, the optimized NVIDIA sine function, and the libdevice cosine function to calculate cosine plus sine of our input. We create a singleton member function, which creates one instance of that module. And then we create a small test in a separate class, which first of all creates an instance of our sine cosine module class. Then we create some random input for X and Y. We use our sine module class file. And then we compare the result to a CPU implementation. So what is interesting here, that it is all generic up to this point, and then you create specializations of that generic transform module, which you ahead of time compile and embed as resources. So again, we could now set the breakpoint here, run the example. I would like to skip that and instead go ahead to some more advanced examples. We would like to show you yet another reduction implementation, which uses a butterfly reduction scheme and a spin lock. So for that, I quickly go back to the slide presentation. So what we want to do is we want to do a reduction with a butterfly scheme, which means we exchange, we have a warp of data here, for instance, and we exchange values in that warp. So for instance, in the first phase, thread 0 and thread 1 exchange their data, and similarly for the others. And in the next phase, thread 0 exchanges the data with thread 1, 2, and so on. And by that, we can actually implement the reduction scheme very nicely in log warp size steps. So now let's have a look at the code. So first of all, I show you the max reduction kernel, so the piece that runs on the GPU. So we have a lock address that is needed to actually do the reduction across multiple warps. We have the input and the result, the reduced values. So what happens here is that all threads, they read in the data from the inputs. So we have exactly the same amount of data as threads that working on this problem. It's a kind of simplified reduction scheme, so a full production version, of course, would need to handle that as well, so that you can use more data than threads in your computations. So the first butterfly reduction scheme that you've seen in the graphics is very simple. So you loop through all of the through the different phases. You have 32 warps, and you increase the index each time by a factor of 2. So you're done in 5 steps. You use an intrinsic warp shuffle XOR to actually exchange the data from between the different threads in the warp. This is a very efficient function. It's a broadcast function. Then you use the internal lit device max function to calculate the maximum between the actual value and the value that you get from the other thread of the warp. And you assign that to the value, and you continue until you're done. So what happens now is that at the end of these steps, value has the maximum of the values in a warp. Now you need to do the reduction across multiple warps, and you do that with an atomic operation, and you introduce a lock so that only one thread can actually update your reduction value. Once you're done, you give the lock back. Again, we create the small test application. So this test only works if your device architecture is larger than 3. So you need compute capability 3.0 for the shuffle instruction, otherwise it will not work. So in our computation, we create 128 blocks, 256 threads per block. We create again the inputs and the same logic, except that we now have to have a variable for the lock, which we allocate as well in device memory. Then we create the launch pattern as well. We launch the kernel, and once we are done, we just get the reduction result from the actual storage location in device memory, which is a single scalar value, and we can write that to the console. So that shows you how you can easily create quite complicated kernels with Alea GPU using advanced functions like warp, shuffles, like locks, like atomic operations. So far, the C# examples. Now I also mentioned that, of course, we have some F# support. F# has offers us the capability to use the quotation-based compilation scheme, and that gives us additional flexibility and additional power to do GPU programming. I would like to show you a Monte Carlo example, which shows you the benefit of using F#. But to start with, let's have a look at the same very basic implementation of the transform that you get used a bit to F#, because in the poll we realized that most of you have a C# background. So let's have a look at the code of the basic transform. Here in F#, you actually work with modules, you open your namespaces, and with a let binding, you assign a value to a symbol. Here, I actually create my worker from the worker default. And again, here is my CPU reference function. In F#, you write functions with arguments in a special form. So you have no brackets. You only annotate the argument with a type. Often you can even omit the type. It is auto-inferred. The compiler figures out the type, and you don't need to add that. So in this example, I would like to add it because afterwards I would use, for instance, this input length method. So I would need to know that this is an array. So this function does the same thing. It takes the inputs, it squares it, and stores it in the output. Of course, this is not a functional implementation. This is just kind of using an ordinary for loop, and we've done that to show you how close the implementation is then on the GPU. So the GPU kernel that we write needs a further attribute. It needs to have the reflected definition attribute so that the compiler creates for this piece of code the syntax tree. And we add the ahead of time compile attribute so that this resource is embedded in the assembly. So again, square kernel, we have the outputs, we have the inputs as device pointers, and the length, an integer. We have all of our CUDA language elements, block index, thread index, block dimension, string threads, and all what you need. And we loop again, we calculate the start, same way. It's a mutable variable here. So typically, if you just use a let binding, the variable is not mutable. You can't change it. You can just assign a new value to it, but not change it. Here, we want to have a mutable value so that we can actually use this while loop and update I with the stride and continue as long as the array that is stored in the argument n. The glue code is very similar. So it's a function again. We have the inputs, a float. We use worker malloc. We create our grid size, the launch parameters, and then we launch the kernel. So here there is a difference. You see that we use this kernel within these strange delimiters. And these delimiters actually tell us that this is actually a quotation, which means it's code which is compiled to a syntax tree, and later on we use this code in the compile process and transform it to LLVM IR. So this function is never being executed as such on a CPU. We just let the F# compiler in its first compilation step to create the abstract syntax tree, which we then convert to LLVM IR and PTX code. After we've launched the kernel, we use gather on the output to return the results. Again, a simple test function to actually run that piece of code. So that's how you write GPU kernels in F#. I have just a bit 4 or 5 minutes to go through now the Monte Carlo example. The Monte Carlo example is a more advanced example that comes from finance. It simulates a stock process with a log normal random walk. So it works as follows. For each time step, we simulate a Gaussian random variable, and we use that to update our existing process or our existing stock value with the following formula. So S is the existing actual value. We go forward dt in time. We have arguments mu and sigma, which are parameters of our stock dynamics, and dw is the Gaussian increment. It's a random variable, a random element, which somehow it describes the uncertainty in the future stock value, and we use this expression. So what happens is we take S and multiply the actual value of the stock, and we multiply it with x of dt times a drift component and square root dt volatility. Sigma is a volatility parameter times our uncertainty. So that's the step-by-step process or function that is happening to go forward one time step of length dt. Again, this code is decorated with the reflected definition attribute. And now we need to write a loop which does this Euler steps many times over multiple time steps, and then also over multiple samples. We want to run that many, many times, so we have a single start, say today, and from there we want to extrapolate many, many different passes of our stock process. So that's the goal. For that, we have this MC loop function, and here you can see that the arguments of these MC loop functions are not just any ordinary data types, they are actual functions. A function is described with the argument and the arrows. So dt is a function that takes an argument of type step and produces a real number. And sigma is a function that takes a step, which is the time location, and a real value, which is the level of the stock at that time level, and produces the volatility, because volatility is now state and location dependent. And the dw is a function which depends on the step, and it just returns a real value. So here we actually abstract how we pass in the data, and instead of actually giving us concrete data types, we use functions, which give us flexibility to use the data in global device memory, in shared memory, or using textures. So inside this loop function, we actually use now this Euler step from T0 or T start to T end, and we do that multiple times in our for all function. We do that n times for n samples. Again, here we have abstracted the sample f as a function. And the Monte Carlo simulation then is our final function that we ahead of time compile. And again, here we pass in actual data or actual data types. And on the fly, we create our functions to read the data, and we pass in these lambda functions to our MC loop, and from there on further to the Euler step function. So this abstraction gives you additional flexibility and allows you to program CPU and GPU code very much alike. Then you need to launch parameters as before. You set up an example function which sets parameters, and then worker, you create random variables, store them in a buffer. You pass on this buffer then to the actual MC sim function, which does the job, and you create all the simulated values back to the CPU. So that's how you can work with F#. Now, a lot of examples can be found in our tutorial. So that these examples that I showed you only explain the very basic steps. Much more can be found on the tutorial. This tutorial project is available on GitHub, so you can download the code and experiment with it. It contains a growing number of examples. Some of the examples are pretty advanced. For instance, we have an n-body simulation example which visualizes the results directly. We have a random forest machine learning algorithm which uses GPU acceleration and also offers a CPU reference implementation. We have an example how to use QDNN, how to use cuBLAS. We have a pretty neat example which is a heat PDE solver, including three-dimensional visualization in with DirectX. We have a tridimensional solver, and you have several examples in C# and F#. Still, the bulk of the examples are in F#, but a growing number of examples can be also used in C#. You find additional information about Alea GPU in the manual as well. So in the section compilation, you find how to install Alea GPU, how to use the license manager. We explain in detail the three different coding techniques: the method-based, the simplest one; the class instance-based, the one that we've seen in the transform example. And then there is a third one, which is pretty useful for library designers and library builders. It's the workflow-based GPU coding, which is only available in F#, and it's more advanced than the class instance-based approach. It's very well suited for complex advanced libraries. We've actually used the workflow GPU coding style to port a few of the NGPU and CUDA unbound GPU algorithms to Alea GPU. Then we have a blog. On the blog, you find regularly posts which explain examples and give you insights in Alea GPU. Just recently, we released the blog about the GPU acceleration in the random forest algorithm. Before that, we actually released several blogs about particle simulations, and the Monte Carlo example that I just showed you, you can find additional details also in the blog. It explains how random numbers are generated with Alea unbound GPU random number generators, and it explains you more about actual mathematics behind that Monte Carlo simulation. So if you have further questions, there is a frequently asked questions section, or you can ask a question either on GitHub or on Stack Overflow, or directly mail us the question. So let's go back to the presentation. I've seen several questions popping up. Let me try to answer them now. So one question is, what are the limitations on functions that can be called within kernels? We can call some functions, but in the kernels, they have to, of course, conform from an argument point of view, so you can't use, for instance, .NET types like arrays, maps in that function, and you have some limitations what you can do in the kernel. Apart from that, you can call functions. So the next question is if one can actually reference non.NET code, such as COM. No, that does not work because COM would call out to some native code which we don't see. So whenever we actually create GPU code, we have to have IL code or quotations which are feasible to be compiled down to GPU code. So that means it must be, it should not call additional .NET type, .NET functions, like for instance an array sort, which would call out to possibly a native code which we don't see and which we can't convert to IR. So COM would not work. So closures are handled partially. It depends on the situation, but here I would actually need to ask the developers more precisely, and I could follow up on the details on how closures are handled. Closures work in most cases, but not over multiple instances of functions. So now about performance, another question is if we have performance statistics comparing the CPU execution time and the GPU. So typically, this simple transform or basic transform example is only faster on the GPU if the array is very, very long, which means if it's in the range of 1 or half a gigabyte or a gigabyte. So it should fill up pretty much all of the GPU memory. Then it makes sense to actually use GPUs. Otherwise, the cost of moving the data down to the GPU and launch the operation is too costly for a very, very basic, simple operation on the GPU. Of course, if the actual computation per thread is more heavy, then again, it's more attractive to move the computation to the GPU. What we can say from a performance point of view is that, of course, Alea GPU, in Alea GPU, you have to pay a certain penalty to actually call the GPU function because you have to marshal the arguments from the .NET memory to unmanaged storage and then actually call the kernel launch through the driver API. So there we lose a bit of time. It's minimal. But as soon as you actually run the kernel, we have pretty much the same performance as CUDA CC++, because we use all the same optimization paths that are used also in the NVIDIA CUDA CC++ compiler. We have there no loss. So we only have a small penalty, marshalling penalty, when calling the actual kernel. So another question is, does Alea GPU handle unsafe code or unsafe kernel methods? No, that does not work. So all the code that you actually want to compile the GPU should be able to compile to IL code that we then can transform to IL. So you can't actually call out to unmanaged code. Now, another interesting question is about OpenCL support. In principle, it is possible now because OpenCL has now as well an internal representation. Spear 2.0 is now available, It's being implemented by several providers like Intel and AMD. So in principle, yes, OpenCL could be supported. From a business perspective, it's not that attractive at the moment, but that might change. It would change if also more mobile devices would support OpenCL. Then, of course, OpenCL is very attractive for us too. But currently, there are no plans to support OpenCL, but it would change as soon as the OpenCL support is more widely accepted in other devices. So inline ASM support, we have a similar thing. We have an attribute builder concept where you actually can extend the compiler and infuse special code segments which produce IR code, which is pretty much what you mean with ASM support. So yes, that is existing already. It's for the experts only, but if you see a use or a need for that, we can certainly support you and help you to work it out. Now, there is a question about the licensing scheme. So we have a free community license. The free community license works for consumer GPUs, for a single consumer GPU, a GeForce GPU. If you wouldn't need to have, or if you want to run code that you compile either just in time or ahead of time, and you want to run it on an enterprise card such as a Grid or a Quadro or a Tesla card, you would need to have a commercial license. And the commercial license, there is a very attractive one for single developers, and there is a small runtime fee for the commercial license in terms of number of CUDA cores. Then there is a more advanced commercial license scheme which has priority support and gives important clients access to the compiler development so that they can actually influence the features that they need to have in the compiler with the next release. So I think these are pretty much all questions that I've seen in the chat box. Unfortunately, the chat box disappeared while I was sharing the screen, so I couldn't see the chat box anymore. So therefore, I couldn't answer the questions during the presentation while they came in. So if there are more questions, feel free to write us an email. Of course, we can answer these questions as well on Stack Overflow. Just post them on Stack Overflow and add the label Alea GPU, so we will see them and we can answer them as well.